Yeah? Okay, great. Yeah, this talk is about fast coalgebreic Bisimilarity minimization. So this is joint work with Thorsten, who used to be at Radboud, but now he is at FAU. This work actually started before he went to Radboud because I read his previous work on coalgebreic Bisimilarity minimization and found it very interesting. Then we started chatting over email, and we noticed that Thorsten was coming to Radboud. So then after that, it really started. So what is this all about? So as you well know, there are many different types of automata. DFAs, free automata, probabilistic automata, transition systems. And for all of these automata, we have algorithms to minimize them, so to merge equivalent states. And these algorithms usually do something depending on the automaton. So you can see, for example, in the probabilistic automaton, you may sometimes need to add up these probabilities when you merge states. And this doesn't occur in the DFA, for example. So the algorithm does need to do something else. But coalgebreic Bisimilarity minimization somehow gives you a single algorithm that can apply to many different automata and equivalence relations on the state. Does anyone know how to remove that black box? Okay. Maybe. Okay. Yeah, okay. So what is the contribution of this paper? It's a fast and general algorithm for minimizing automata. And what do I mean by that? It's general in the sense that it works for any computable coalgebra. So computable here means that you can compute the functor operation in a certain sense. And we also need to be able to determine the predecessors of a state. It has decent asymptotic complexity, so it has complexity m log n, where m is the number of edges and n is the number of states. And we have an additional factor phi of f, depending on how long this functor operation takes. This is a little bit slower than previous algorithms, but the nice thing is still has the right complexity in terms of m. So it's fast in practice. So we will show later that, at least in our benchmark, we don't pay any penalty for using a generic algorithm. And it uses low memory, which is important because many times the constraint is not the speed, but the constraint is how much memory you have, because it's actually quite fast. So you usually run out of memory before you run out of patience. So what are the types of automata that this works for? So it works, for example, for DFAs. And to specify DFAs, you only need to give this functor. And that then fully specifies whether the DFA is somehow. And it also specifies the language equivalence on it. Similarly, for transition systems, we have a different functor. And then you get a different type of automaton with a different type of equivalence on the state. So not all types of equivalence can be handled like this, but the type of equivalence that we call strong bisimilarity in a certain sense. And another nice thing about this approach is that you can come up with your own automaton type by composing functors. So this way you can easily invent your own automata and minimize them. So let's look in a bit more detail. On the left here, you see a DFA. And usually we draw that with a picture. But here we want to think about that as the list of information below. So instead of thinking about a graph with edges and labels on the edges and so on, we think about all the data being attached to a particular state. For example, here, state 1, we attach a triple. So the F for false means that it's not accepting. And then the 2 means that the A transition goes to state 2. And the 3 means that the B transition goes to state 3. Similarly, for the transition system, we attach a set to each state. And it's important that it's a set and not a multiset. So if you did a multiset, you would also get an automaton, but you would get a different equivalent on the state. And on the right, you see a Markov chain. And there we have a probability distribution over the outgoing edges. And that then gives us this behavior that if you merge states, then you add up the probability. Okay, so let's look at which states are equivalent here. For example, in the DFA, 4 and 5 are equivalent because they accept any language. And 2 and 3 are equivalent because on transition A, they step to 4 and 5, which we already saw were equivalent. And on B, 2 steps to 3, and 3 steps to itself. But if we assume that they are equivalent, then indeed the transitions, then you also conclude later that they are equivalent. So sometimes you need to assume that states are equivalent, and then if you can't disprove that, then they are equivalent. For the transition system, it's a little bit different. So here we initially distinguish state 5 from the other ones, because state 5 is the empty set, and the other ones are definitely not the empty set. So state 5 is definitely different than the other ones. But then state 3 and 4 are the same, even though state 3 has 3 transitions. If we assume that 3 and 4 are the same, then those 3 and 4 in the set, they get merged to a single element. And a similar thing happens with the Markov chain. So what is Coalgebraic Bisimilarity Minimization? As input, we give a functor, which describes the automaton type. And we give a coalgebra, which is such a mapping from a finite set of states to the data attached to each state. And that then represents the concrete automaton. So what do we get as output? We get a partition, which says for each state, what is its equivalence class? And this has to satisfy some condition, which says that we didn't merge too much. So this says that if 2 states get placed in the same equivalence class, then up to this partition, they have to have the same outgoing transition. And we want to get the number of equivalence classes as small as possible. So I will now sketch how our algorithm works, which is actually very simple. So initially, you assume that all states are equivalent. You pick an equivalence class. You split the equivalence class by signature, which are these things that I showed before in the table. After replacing them, replacing the outgoing transitions by the current equivalence classes that you have. And that may involve some normalization, for example, removing duplicates from the set or merging 2 probabilities together. And you just iterate this until convergence. So this algorithm is a bit naive. So what we want to do is to only recompute the signatures of the states that changed. And it turns out that if you schedule this algorithm in a particular way, then, and if you make sure to never loop over the unchanged state, which is actually a little bit tricky, but it can be done, then you get a fast algorithm. But in a way, this is much simpler than previous algorithms for this problem. So let's now look at how that works in detail. So here we have our DFA. And initially, we assume that all states are equivalent. So we just give them all state number 1. Then we pick an equivalence class, which we have only one, so we pick that one. We compute the missing signatures. So initially, we didn't have any signatures, so now we compute them. And now we see that we split the original equivalence class into 2, because the top 3 states start with F and the bottom 3 states start with T. So they have to be in a different equivalence class. So what we then do is we assign new state numbers to one of these 2. We pick the bottom one here. And we also remove all the signatures that are now invalid. So all the states that have incoming transition to the states that change, they are now invalid. So we remove them, but we keep the one on top because this didn't change. It was F11 before, but still F11. And we iterate this process until convergence. So now we pick, again, an equivalence class and compute its signatures. So we pick 2, for example. And now we see that the signatures are still the same, so everything's fine. So now we pick equivalence class 1. We recompute the signatures. Now we see that in equivalence class 1, we have 2 different signatures, namely the top one has a 1 and the bottom two have a 2. So again, we do the same. We change the state numbers there. And we continue. And then eventually we converge and we found our equivalence classes. Let's now do that on a transition system. So we do the same thing. We start with all states in the same class. We compute the signature. We see that the state on the bottom right is the empty set, the other ones are not. So we need to reassign some state numbers. So we do that. That invalidates some. We recompute them. We invalidate some more. And then we converge. So I have to say I oversimplified a little bit, but the real algorithm is not complicated. The only complex part is to make sure that everything runs in the right complexity by not looping over the unchanged state. So this requires some bookkeeping, but this is also not complicated. So what do we need from the automaton to do this in general? So we need some function that recomputes the signatures given the new state numbers of the other state. And we need the ability to determine the predecessors of a state. And then let's now think about how long that will take. So I claim that this does m log n signature computations, but where m is the number of edges and n is the number of states. Why is that? Well, let's think about how many times does a state's number change in this process. So it changes when one of its so each time a state number changes, we may need to reassign the equivalence classes. So if we make sure to reuse the old number that the equivalence class had for the biggest one, then it turns out that the state number can only change log n times, because each time your state number changes, it means that you were at least in the smaller half of the equivalence class. So the equivalence class that you were in gets cut at least in half in each step. And this is called Hopcroft's trick, and this is the basis of almost all efficient automaton minimization algorithms. So how many times does the signature get recomputed then? Well, it gets recomputed when the state numbers of one of its successors changes. So if that happens log n times, then the state number changes at most log n times per edge in the automaton. So that's why we get this many signature computations. And then the total complexity of the algorithm is usually k m log n, where k is the size of the state, because usually this signature computation can be done in linear time. But in general, it takes some kind of factor times m log n. So what about the complexity of all this bookkeeping that we would need to do? Well, we need to use a partition refinement data structure, which supports n-way splitting, because in the examples that I showed, everything always split into 2 classes, but it can, in general, split into n classes. And this is the only part of the algorithm that's a little bit complicated. So let's compare this with previous work. So there's Copar. This works for Coalgebraic automaton, but it has a slight restriction to zippable functors, which is a technical restriction. But the complexity asymptotic complexity is very good. So it is faster than us even, because this zippable restriction gives you the ability to do more than just call this functor operation, which means that you can remove this extra factor, phi of f. Then there is a distributed Copar. So that is a distributed algorithm that you can run on a cluster of machines. So that one is asymptotically slower. It's quadratic, so that's not not so nice in certain cases, but for some automata it doesn't matter, it still runs in linear time. But for other automata it will be very slow. And then there's MCRL2, so this has very good asymptotic complexity, and but it works for LTSs. I have to say it does work for equivalence relations that we cannot handle, like branching bisimilarity. But for strong bisimilarity, they have a very good C++ implementation of various algorithms for that. So then our tool, which is called BOA, this has this extra factor f, phi of f, but it works for pretty much all coalgebras, like this DCPR. But the asymptotic complexity is still log n. We wrote this in Rust, and the first two are written in Haskell, and MCRL2 is written in C++. Let's now look at some benchmarks. First, I compare with the Coalgebraic tools. So I use the benchmark that they use in their paper. And there are many more benchmarks, but I couldn't fit them on the slide. So we will just look at the biggest ones. So you see here, first of all, CoPar. There are some entries missing because they are too big to handle for CoPar, and 16 gigabytes of memory, and probably even more would not be enough. Then DCPR does handle them because it's running on a cluster, so it has a huge amount of memory available to it. And then in the third column, you see the time of our implementation. So you see that it's quite a bit faster than the other ones. In terms of memory usage, so these benchmarks that CoPar could handle, they were selected to make it use 16 gigabytes of memory. So it uses 16 gigabytes in each case. So DCPR was run on for these benchmarks on 32 nodes. So the memory here is listed. You have to multiply it by 32 to get the total amount that is used. And then in the final column, you see how much memory we use. So it's quite a bit less. So it means that you don't actually need this big cluster. You can just run it on a laptop. So then let's see what is the cost of doing this general algorithm instead of a more specialized one. Of course, we cannot make a general conclusion about this, but here's one example. So I think MCRL2 is quite a good tool. Our reviewers actually pointed out that we should compare to it because there's not really my skill. I did not know that initially, but now I know that this is the one to compare to. So you see here that actually we are still faster than it. And this is maybe a little bit surprising because asymptotically we are slower. But it turns out that this fast asymptotic complexity requires some very fine-grained tracking of which things change. And this is quite slow on a real computer because it requires random memory accesses everywhere. Whereas we are slower by this factor of phi of f, which requires recomputation of a signature, but this is quite fast because this is a very local operation in memory. And the advantage there is that one such operation could potentially split your equivalence class into many classes, and in practice this really happens. Whereas with the fine-grained tracking, you will have to split a lot of times to get the final effect. Yeah, so MCRL2 has many algorithms implemented, but in each case we compare with one that was the fastest on that, and I think it was the same on all benchmarks except one or something like that. So to conclude, I claim that minimization can be generic and fast. Of course, to fully satisfy this claim, we would have to compare to all the other specialized algorithms too, which we are working on that. So in particular, we want to integrate it into Storm. We are working on that with Sebastian Jungs, or will work on that. And we also want to see if this algorithm can work for other notions of equivalence, like branching bisimilarity. And one thing that is not very nice about our implementation currently is that it is not specialized on the type of automata. Even this phi of f signature computation is not specialized. So we think we can do something there by using Rust's generics, which the compiler automatically specializes. By using that in some way, we think we could get a specialized version for each automaton. So you create some generic type, and by instantiating that, you get a specialized implementation of this signature computation. And then it may be faster. That's my talk. Thank you.
Thanks a lot. Any questions?
So my co-author is also on AirMeet, so you can also ask questions to him, but he's impersonating me, so you have to.
Okay. Yeah.
Could you give an example of a functor or system type to which the old algorithm does not apply?
Yeah. So I can go to my list. Right. Yeah. So Thorsten's algorithm does apply to all the ones on the top. It does not apply on the bottom row. Also, it does not directly apply to if you compose two functions. So even the functors above you, it does not directly apply to it, but you can do some pre-processing of an automaton to somehow split a composition. Whenever you have a composition in your functor, you split all the states into one state per level of the composition. And this is also kind of what makes the difference in the runtime, because that way you get many more states and many more transitions. So although it can be handled, if you handle it that way, then it's not very fast anymore. It's still asymptotically good, but yeah, not in the actual time in seconds that you get. But I have to say that, maybe for all the automata that you would actually want to do it for, most likely it has out and works. You could run it.
Any further questions? You mentioned on the last slide branching by similarity. What's there the technical challenge? And I'm asking this because for Markov chains, it has taken up to very recently to come up with an algorithm which is in the same complexity, so n block n. Are there any hopes in your setting to get a similar complexity as you have to drawn by similarity?
Well, so I think our complexity is already not the best, so it has this extra phi of f factor. So I don't.
But would you be? Do you think that you would be able to have branching by similarity with a similar, let's say, phi f? I'm happy to pay the phi f extra.
Yes, okay. I think.
Anything, which is
yes, I think you. So I'm not completely familiar, but you know this. So branching by similarity, that does fit into the signature composition framework, right?
Yeah.
So then it would depend on what is this phi of f in that case. So I think the main difficulty there is just implementing it actually and seeing what this phi of f actually is.
It's complicated phi.
Yes, yes, yes.
Yeah. By the way, please mention your name and affiliation.
Hi, Jules. Great talk. Thank you very much. I'm Wojtek from UCL, and I was wondering, what are the actual challenges of adapting to coalgebras in different categories instead?
Yeah, we are also thinking about that. I didn't list it in the future work, but I don't know yet. I don't know. Maybe Thorsten can give a better answer to that actually. But you will have to ask your question on AirMeet.
Any other questions? I have one more. implicit state representation of, let's say, the labor condition system or market change or whatever. In many different model checkers, you also have the model in a symbolic way.
Yeah. Yeah.
Are your algorithms, or is your algorithm, let's say, also generalizable to work with symbolic perspectives?
Yeah, it's a good question, but I don't really know. So there you would have to. Yeah, so I can give some kind of indication that it might be, but I'm not sure. So it's speculation. So the main point here is that you need to recompute a whole bunch of signatures. That's the main step. So that seems like something you could do symbolically, maybe. But then whether you could do all the other things still fast, I don't know.
Okay. Jan, thanks for attending the session. Apologies again for the situation here with the thing. I hope they will fix this after the coffee break. And thanks to speakers.